Okay, folks. In today's lesson, we're talking about inverse relationships. So the ideal is that you're here and you can chat with somebody. But since obviously the ideal never quite happens right now, these questions, I'm going to go through their answers kind of on the next slide. I just didn't want to open the presentation and not have anything there because there's no date or title or anything once I flip the slide. So basically, we're going to go through the type of notation that we use for an inverse. We're going to discuss whether or not the inverse of a function produces a function. Talk about how to find an equation or to draw the graph. And then just the relationships between domain and range of a function and an inverse. And restrictions on domains to make sure that the inverse is a function. So all of this should be basically the same as what you guys learned in grade 11. So the hope is that this lesson is kind of like a little breath of fresh air. It's something you already know. You just have to remember it, okay? So if we want to indicate that something is an inverse function or a relation is the inverse of a function, we use that little -1. So the notation for F inverse is that, okay? And if you wanted to say it in words, it's like F inverse of X or at X, okay? And when I ask if the inverse of a function is always a function, I would ask that you think about probably your most popular function that you used the most in the last couple of years, y equals x squared. So if you recall from last year, the inverse of y equals x squared is like x equals y squared. So it would be something like that. It would have been good if I used function notation up here. But here, just pretend that was f at x. So f inverse at x is sideways. And we can see that that fails the vertical line test. So the inverse of a function is not necessarily a function. Okay, so not necessarily. A good way to check, do a horizontal line test. Horizontal line test on f at x. So if you only have the graph of f at x and you're trying to figure out if the inverse is a function, if the regular function fails a horizontal line test, so if a horizontal line hits 2 points, that means that your inverse is going to fail a vertical line test. So you can figure it out from the parent graph rather than worrying about the inverse. So now it's saying, what can you do so that the inverse of a function is also a function? And again, this is something that you would have seen last year, but basically what you want to do is restrict the domain. I'm going to put or range in brackets, but that's not something you would do very often. So restrict the domain of the original function. So that you're only working with kind of half of it so that you don't have any repeated values. So restrict the domain of the original function so that it does pass. Okay, and we've been doing this without really telling you with the square root function, right? Because that is just half of a sideways parabola, which is an inverse of a quadratic function. And the way that we're doing that is just by always only considering the positive root to get you your square root function, right? But if it was this, you'd be thinking about the positive and the negative root. So again, work with the original function to restrict the domain just because that's typically the one that's more familiar. So for y equals x squared, we would want to say that we're only going to think about the domain that is either to the right or to the left of the 0. So x is greater than or equal to 0, or x is less than or equal to 0. So if I think about one side or the other, then again, so like this would be the one that I just did in blue would be less than or equal to 0, and it would come down here. Okay, or the other side would be this one, so that's your greater than, and that would be the top arm of your inverse. Okay, because then that produces just half or just a square root function, and then that is a function. So if you have to make your inverse a function, just restrict your domain to eliminate those repeated y values, because the repeated y's become repeated x's when you take the inverse. So now to talk about how to create the graph of an inverse relation. When you have a graph of the original function, so like this pink line, you can totally reflect it over the line y equals x, which is all that happens here too. You have y equals x running through here, and then your inverse has been reflected over it. So reflect over y equals x. So that's just a line with a slope of 1 through the origin. So if you're trying to visualize, you just want to take points and flip it. If you're given a table of values, you're going to just switch the columns, right? Because the whole idea of an inverse is that you're switching your x and your y. So the x values become y values, and then the y values become your x values. Okay, and then if you guys are given an equation, what you're going to do is switch x and y, and then re-isolate. Isolate y, and then write f inverse at x in place of y. Okay, and we'll do an example of that so that you can remember, but hopefully this all sounds familiar. You might have forgotten some of it if you had math a long, long time ago last year, but this is nothing new. I didn't introduce anything that wasn't part of grade 11 there. Okay, so if I want to find the equation of an inverse relation, here's the mission. Switch x and y, isolate y. Okay, so just make sure that you do good math when you go to isolate y. So you replace the f at x with y. So y equals x cubed plus 3. Then I'm going to switch x and y. So I have x equals y cubed plus 3. Now I have to isolate y. So I'm going to bring my 3 over. So x minus 3 equals y cubed. Okay. And then I'll come up here. I have to take the cubed root to isolate y. So y would equal the cubed root of x minus 3. Okay. So that's my inverse. You don't want a plus minus in front of a cubed root because you can actually take the cubed root of negative numbers and stuff. So the answer is just going to have the sign of whatever was underneath. But there's no like ambiguity. So when you're dealing with an even root, you don't know what was squared or what was raised to the power of 4. With something cubed, you definitely do know, right? So you know that a negative value is going to produce a negative cubed root, and it couldn't have been the positive number. So when it's an odd index in your radical, you don't have to worry about plus minus. It's only when it's even. Okay, so that's your inverse. If you had to draw it, you could. It's just the cubic function reflected over y equals x, so it's kind of like a sideways cubic function. When we're talking domain and range, again, work with the original function because the domain of the original function is the range of the inverse function. Oh, I should finish with my notation here, sorry. Let's put f inverse in there so that we know what we found. Okay, so the domain and range basically just switch. So domain of f at x is range for f inverse at x, and then the opposite is also true. So the range of f at x is domain for F inverse at x. Okay, and then this is just an example to kind of work with restrictions. So we have a quadratic, again, you did the inverse of quadratic relations last year, but the first step is to find an equation for the inverse. So again, you're going to replace g at x with y. Okay, and then we're going to switch x and y. So we have x equals 2 times y minus 1 squared plus 3. Now bring your 3 to the other side. So x minus 3, 2 times y minus 1 squared. Okay, and then divide by 2. Okay, so that's kind of, we're getting there. We have to take the square root to eliminate the brackets. And when you do that, make sure you think about the positive and the negative. So I'm just going to write this with the stuff on the other side. So you'd have y minus 1 equals the positive or negative square root of x minus 3 over 2. Okay, and that's fine. That works. And then we bring the 1 over. Okay, so I'm going to, in one step, replace y and write my equation. So 1 plus or minus the root of x minus 3 over 2. So that's my new equation. And that's all fine and good. I don't really know what that looks like, and I don't really care to think about it to try to graph it. So when I go to graphs, it says sketch the graphs of g at x and its inverse. Draw the first parabola, because we talked yesterday how to do that quickly, and then just switch your x's and y's in some of the points and put it on the other side. So if I want to draw g at x, all that you need to know is that your vertex is at 1 and 3, and it opens up. Okay, and then a is 2. So I'm going to go 1, and then 1, 2, 3, right? And then a is 2. So I'm going to go over 1 and up 2, and left 1 and up 2. And those 3 points are sufficient to show me the original function. Pretend like that's drawn better. Okay, so that's g at x. Now, if I want to draw my inverse, I'm just going to take this point. So this point right here was at 1 and 3. So that means that my inverse, so for g inverse at x, I don't really want to call it a vertex, I guess, but it is, right? So that vertex is going to become 3, 1 for my sideways parabola. And then I had this point here at 2 and 5, so that would be 5 and 2. And then I have this point here at 0 and 5, so 5 and 0. So then when I go to draw this, I can just put it in here using those 3 points. So 1, 2, 3, and 1, and then 5 and 0, and 5 and 2, and now I flip that graph on its side. Okay, so that's how I would graph my inverse. If you're good at visualizing things, you can also work with just reflecting over y equals x. I just struggle with like diagonal reflections myself. Like I don't have a good, I guess spatial reasoning is the thing I have the worst time with. So, but you absolutely can reflect over this line as well, if that's something that you can visualize easily. And some people can. Okay, so that's the other option. You can do a reflection. I usually just, in my head, switch some points to move it, though. Okay, so that's part B done. And then part C is saying state the restrictions that we would apply to the domain of g at x so that its inverse is also a function. So this is kind of what I talked about earlier. You want to restrict the domain at the vertex. Okay, so I can pick over here, right? So the orange would be where x is the element of real numbers such that x is greater than or equal to 1. So it's always the x coordinate of the vertex where you want to restrict it. This would reflect to this part. Okay, so that would be what your graph would look like if you use the positive case. So that would be like the plus. And then your other option is here, right? So those are the two pieces that you're able to work with up there. So or d equals x is an element of the real numbers such that x is less than or equal to 1, and that would just be this bottom piece. Okay, so either one of the halves of this thing is a function, but when it's all together, it's just a relation. So again, hopefully that was like nothing new, except for maybe the cubed root, because you probably haven't found the inverse of a cubic function, but the rules stay the same. But that should, I hope, feel like kind of a better day than all of the vocabulary and the big chart and stuff that we did yesterday. So hopefully we remember that, and this section will be kind of fun to work on.